Welcome. Today we are going to cover two things, that is Galerkin's method of weight residuals and how to apply this Galerkin's method of weight residuals to formulate finite element equations. Galerkin's method of weight residual is extremely useful in solving engineering problems where governing differential equations are readily available. We can say that this is an approximate method to solve the differential equations. Galerkin's method of weight residual is an effective tool for FEM formulation of a field problem which is governed by differential equation. The Galerkin's method of weight residual start with a governing differential equation for a field problem. Now let us suppose this is our governing differential equation. D of u is equal to P, where D is a differential operator. Now our task is to find out the solution for u. Often this u is a field variable. If it is a structural problem, then the field variable will be displacement. If it is a scalar field problem, for example, if it is a problem of determining the heat transfer rate, then or thermal problem, then this u will be temperature. Now we will assume a trial solution u bar of x. This trial solution is such that it is not the exact solution, rather it is the approximate solution, and our job is to formulate or to find u bar in such a way that it will be very close to the exact solution. Though it is approximate solution, you have to find out, or you have to come up with such type of trial solution that will be very close to the exact solution. So I will now write u bar of x is equal to summation I is equal to 1 to n ci into ni of x. Depending upon the value of n, there will be n terms in your trial solution. Here ci denotes the unknown coefficients which are to be determined, and ni of x is a function of x. Why I am writing function of x? Because right now I am considering only one dimensional problem where your field variable, let me show it here, where your field variable is only function of x. Therefore the derived quantities, for example, if field variable is a displacement, the displacement will be function of x, and all derived quantities like strains, stresses, strain energy will be only function of x. So that's why I am writing here ni of x, that is a function of x. Now if I substitute this trial solution, which is an approximate solution, into our differential equation, then you can see that there is an inequality. Why? Because this u bar is not exact solution. So I can write d of u bar is not equal to p, or rather I can rearrange the term d of u bar minus p is not equal to 0. Now whatever error is left, whatever error is left, this error is termed as a residual, and it is here denoted by rd of x. Let me highlight it, rd of x, that is called as a residual, which is basically an error, because since this u bar is not our exact solution. Before proceeding, let me tell you one thing. There are two types of residuals. One is boundary residual and another is domain residual, and corresponding to these two residuals, there are two different problems: finite element problem and boundary element problem. Now what is the meaning of these two terms? uh, Let us make it very clear. If assume trial solution, does not satisfy the boundary conditions, then in that case there will be boundary residuals. And if the boundary residual exists, then the problem is termed as boundary element problem. So this is not in the scope of our discussion, so we will not consider this. Now in our problem, suppose this is the domain for which we have formulated the differential equation, or we will call it as a governing differential equation, and this is the boundary of this domain. Now whatever trial solution u bar of x that we have assumed, it satisfies the boundary conditions, means there will not be boundary residuals, only domain residuals will be there. And therefore since boundary residuals are zero or they do not exist, our problem is a finite element problem. Or in future, in coming after some after undergoing some theory, we will shift how to apply this Galerkin's method of weight residual to formulate finite element method, or to solve finite element problems. So what I want to say that in our situation only domain residuals are present, and we will be moving to the formulation of finite element problem. Now, according to method of weight residuals, uh, this is the expression integral over the domain. This is the sign for domain. Wix into Rd of x dx is equal to 0, where this Wi is nothing but a weighing function. Now, what should be the choice of weighing function? There may be different choices of weighing functions, but in Galerkin's method of weight residual, our weighing function is a very special function. And what is that function? We will see. In Galerkin's method, the weighing functions are chosen to be identical to trial functions. Here you can see this, we will show it here. This was our assumed trial solution. U bar of x is equal to summation I is equal to 1 to n ci n to ni of x. So this was our trial solution. So here this weighing function is uh, these weighing functions are chosen to be identical to trial functions. So this expression turns out to be integration over the domain ni of x into rdx dx is equal to 0, where I is from 1 to n. It depends upon how many terms are present in your trial solution. So this weighing function is nothing but ni of x, which is the same function which is present in our assumed trial solution. So that was the basics of Galerkin's method, and I introduced this portion only for revision purpose. Else, you might have gone through all this, the way how to apply Galerkin method. So here, consider this example of elongation due to self-weight. So what is the problem? Find the elongation due to self-weight, where a bar is present which is fixed at the top, and other things are shown here. A is the area of cross section, rho is the mass density, material Young's modulus is E, and total length of bar is L. Now using Galerkin's method of weight residual, you have to find out what is the elongation of this fixed bar, which this bar which is fixed at top. Let us apply Galerkin's method of weight residual to this problem. Here I have shown the problem. A bar is fixed at the top, and we will proceed now to, first of all, we need to keep in mind that for using Galerkin's method of weight residuals, we need to find out what is the differential equation of problem. So first step is to derive the governing differential equation for the problem. Let us consider u of x as a displacement, and this u of x denotes displacement of any point having coordinate x. So this du by dx will give the strain, which is denoted by epsilon x, and sigma x, that is stress, will be given by E into du by dx. So force present at any distance x will be A into E into du by dx. Now consider this section, a very small section, length dx at a distance x from the fixed end. A small section have to support the length of bar which is below it, means it has to support the weight of this much length. Here I am showing it. This strip of length dx has to support uh, weight of bar which is below it. Therefore, what is the length of bar below it? If total length is L, then L minus X is the length whose weight has to be supported by this strip having thickness Tx, which is present at a distance x from the fixed support. So multiply this length by area will give you the volume, and if rho is the mass density, rho into g will be the weight density. So weight density into volume will be the total weight of this length L minus x, which has to be supported. So this is nothing but the force acting on this elemental strip, or force acting on the strip having length dx. So equating these two terms, AE into du by dx is equal to rho g A into L minus x. So it is quite simple. You can easily verify this. So governing differential equation is du by dx plus rho g by E into x minus L is equal to 0. Let us assume the trial solution uh, like this: u bar of x is equal to a0 plus a1x plus a2x square. I am assuming a quadratic trial solution. What are the boundary conditions? This bar is fixed at the top end, means u, that is the displacement at x is equal to 0, is equal to 0, and bottom end is free, so there will not be any stresses and strains at the bottom end. So strain, that is du by dx at x is equal to L, is equal to 0. If you apply these boundary conditions, we can rewrite our trial solution like this: u bar of x is equal to a2 into x square minus 2lx. Now upon substituting this trial solution in our governing differential equation, we can find out the error, or call it as a residual. And further applying Galerkin's method of weight residual, we can write integral over the domain. Now your domain is complete length of bar, or it is a complete bar. And w1x into rdx is equal to 0. Why w1 only? Because this is a one-term solution. Consider this similar to ci into ni of x, where ci means c1 is a2 and n of x is nothing but x square minus 2lx. But as you know that in Galerkin's method, this this weighing function is nothing but it is same as the trial function. So here w1 of x is taken as x square minus 2lx, which is same as this term, right? Now as we go on solving this expression, this integral, you can see here that this integral is a function of x and a2. So upon solving this integral, we can see that we obtain this expression, twice a2 plus rho g by e is equal to 0. So a2 is equal to minus rho g upon twice e. Now substituting this value of a2 in our trial solution, we can say that our trial solution becomes u bar of x is equal to rho g by twice e into twice lx minus x square. This is the required solution. Now you can use this u bar of x, which is a solution for the field variable. What was our field variable? Displacement. To calculate displacement, then strengths, stresses. Suppose somebody asks you what is the extension of this bar. So extension of this bar is nothing but total extension at x is equal to L minus total extension at x is equal to 0, and if you proceed by substitution of appropriate values of x, you will get the elongation of bar is nothing but rho g L square by twice e, means weight density into L square by twice e. So you can check the analytical solution and compare this analytical solution with our solution obtained by Galerkin's method of weight residual. And also you can do one thing, you can find out what are the strength, the stresses, and plot the variation of stress that is left as an exercise for you. Let us move to the Galerkin's finite element method. Piecewise trial function approximation of weak form of Galerkin weight residual technique. Means when we apply Galerkin weight residual technique in a piecewise manner and use the weak form of same, it leads to formation of finite element method. Now how does this happen, that we will see. Now we have divided our domain into m number of elements. Previously, whatever trial solution u bar of x that we had assumed, it was valid over entire domain. Practically speaking, it is not possible. And what is our basic philosophy of finite element method? We divide the domain into number of elements. So we have divided our domain into m number of elements. Now let us consider again this governing differential equation is like this, d2y by dx square plus f of x is equal to 0, where x varies from a to b. Now consider this x1 as a and xm plus 1 as b, and boundary conditions are like this: y of a is equal to ya and y of b is equal to yb. Means y when x is equal to x is equal to a is ya, and y when x is equal to b is yb. Let us assume y bar of x as an approximate solution for this governing differential equation, which is of the form summation I is equal to 1 to m plus 1 yi into ni of x, where ni of x are now interpolation functions, and yi are nothing but discrete values of y at nodal points. Means we can say that y is nothing but a discrete value of solution at nodal points, means y1, y2, y3, y4, y5, and so on. Whereas the interpolation functions are shown in the figure. Uh, this is n1 of x, n2 of x, n3 of x, n4 of x. Uh, Here they are shown as a linear function of x. So this is N2, this is N3, uh, N1, N2, N3 and N4 that are shown here. Now here we show how our interpolation functions are represented mathematically. Now ni of x, as you can see, ni of x is written like this: x minus xi minus 1 divided by xi minus xi minus 1, when the variation of x is between xi minus 1 to xi, and when x varies between xi to xi plus 1, ni of x is mathematically represented like this. Uh, Apart from this, outside this range, ni of x is equal to 0. Let's take an example of n2 of x. Within the interval x1 to x2, the n2 varies like this. You can easily see here, n2 varies like this, and within the interval x2 to x3, the same function, same interpolation function varies like this. Here it is shown in a linear fashion. Now consider, for example, consider the interval x2 to x3. Within this interval, how your y bar is represented? It is represented like this: n2 of x into y2 plus n3 of x into y3. Here clearly you can see that. Let me clear it. What was our interval? X2 to x3. Within this interval, two interpolation functions are coming into picture. One is n2 of x, which is varying like this, okay, and another is n3 of x. Within the interval x2 to x3, it is varying like this. So this n2 and n3 are coming into picture when we are considering this interval x2 to x3, and here it is shown how y bar of x is represented within the interval x2 to x3. Now we will substitute this y bar into our governing differential equation, and then we will get residual. This is Rd of x given by d2 y bar by dx square plus f of x. So upon substitution, this Rd of x is like this. We can calculate Rd of x, and it comes to be this much. So in Galerkin's, by Galerkin's approach, here I have used the same. Using Galerkin's approach and using the trial function nj of x, where j varies from 1 to m plus 1, we can write integration over the domain nj of x into rdx dx is equal to 0. We have seen this earlier also, how to apply Galerkin's technique, where this ohm, this symbol represents the entire domain. Now our domain varies from xa to xb. So further simplifying, substituting the value of rd of x that we have calculated here, integral from xa to xb, that is our domain, nj of x into bracket summation I is equal to 1 to m plus 1 d2 by dx square of yi into ni of x, f of x dx is equal to 0. This is simply we have applied the Galerkin's wet residual method. As you see, in any interval from xj to xj plus 1, only two trial functions are active. Active means non-zero. Therefore, we can rewrite our previous equation like this: uh, integral within the limits xj to xj plus 1, which is the domain interval under consideration, nj of x into d2y by dx square of yj nj of x plus yj plus 1 nj plus 1 x plus f of x dx is equal to 0. Now consider the interval. Suppose this is the interval x2 to x3. Within this interval x2 to x3, only two functions are active, means only two functions are non-zero. First one is n2 of x, which is varying like this, and second one is n3 of x within the interval x2 to x3. This is varying like this. So for this interval x2 to x3, only two functions are non-zero, that is n2 of x into n3 of x. So that's why we can again write like this, from interval, for interval xj to xj plus 1, this equation becomes integration xj to xj plus 1 nj of x in bracket d2y by dx square of yj into nj of x plus yj plus 1 into nj plus 1 of x plus f of x dx is equal to 0. For example, consider j is equal to 2. So from interval x2 to x3, our equation becomes for j is equal to 2, n2 of x into d2 by dx square y2 into n2 of x plus y3 into n3 of x plus f of x dx is equal to 0, because for this interval only n2 and n3 will come into picture, all other interpolation functions will be 0. For one single element which is having two nodes xj and xj plus 1, this equation represents set of two simultaneous equation. For example, when j is equal to 2 and when j is equal to 3. For j is equal to 2, we can write one equation, and j is equal to 3, we can write another equation where 2 and 3 are nodes shared by one single element. So these simultaneous equations represented by this equation are further written in the matrix form, like sum matrix. Right now I don't know what is this sum matrix, into y is nothing but uh, nodal values of y, means y at x is equal to xj and y is equal to y when x is equal to xj plus 1. So this matrix, this sum matrix into this y matrix is equal to another some unknown matrix. So right now, what will be these two matrices? Yet it is not clear. As we proceed, it will become clear how these two matrices that I am talking about, how they will be represented. Now we will move towards element formulation. Again, consider the domain which has been divided into m number of elements. Here it is shown. Now consider specific domain from x varies from xj to xj plus 1. Here it is the complete domain, and here it is the specific domain that we will now focus our attention. Again, the governing differential equation will be same, d2y by dx square plus f of x is equal to 0, but the domain under consideration is this domain. Again, now let the approximate solution for this interval be y bar of e of x is equal to yj into capital N1 x plus yj plus 1 into capital N2 of x. Now these interpolation functions are written as capital N1 and N2, uh, and y bar is now written as y bar e, or this e subscript, this e stands for elemental solution. Since we are dealing with one single element which varies from x is equal to xj to x is equal to xj plus 1, so that's why we have used this letter e here. So y bar e denotes we are talking about one single element. So y bar e of x is equal to yj into capital N1 of x plus yj in yj plus 1 into n2 of x. Now we have used n1 of x and n2 of x. Now our element is varying from xj to xj plus 1, and the length of element, suppose the length of element is le. This le stands for length of element. Here n1 of x and n2 of x, the interpolation functions specific to this element, are also shown here. You can easily see that these interpolation functions, as I said earlier, that for any interval xj to xj plus 1, only two interpolation functions that we have seen earlier, not these interpolation functions, are non-zero. So this n1, capital N1 and n2 are overlapping portions of the previous interpolation functions that we have seen. uh, these are nothing but the overlapping portion of those interpolation functions. So here n1 is varying like this, and here n2 is varying like this. So if you look at this, the way I have shown the interpolation function capital N1 and N2, these are nothing but the overlapping portion of the interpolation functions that we have seen earlier for this interval xj to xj plus 1. Now you are all aware about what is a global coordinate system, what is local coordinate system, and what is natural coordinate system. If we use local coordinate system, in that case, this xj plus 1 minus xj becomes le. Simply what I am doing, I am substituting xj 0 at xj 0 here, and I am substituting le here at xj plus 1. So as x varies from xj to xj plus 1, in our local coordinate system, it varies from 0 to L. So xj is equal to 0 and xj plus 1 is equal to Le, where Le is the length of element. So 0 to Le is your local coordinate system. So clearly you can verify that n1 at xj is equal to 1, and at xj plus 1 n1 is equal to 0. Similarly, n2 at xj is equal to 0, and at xj plus 1 n2 is equal to 1. In other words, interpolation function n1 at local node 1 is unity, and at other node it is 0, and interpolation function n2 at local node 2 is unity, and at other node it is 0. Now substituting this trial solution for one single element, that is y bar of x, we get our residue like this. This residue becomes d2 by dx square of y bar e of x plus f of x. Now applying Galerkin's method, we can write like this: the integral over this interval, capital Ni of x into this residue is equal to 0. This is nothing but the Galerkin's method, which is rewritten in this way. Now we will apply integration by parts. This is very important. We will apply integration by parts. After applying integration by parts, you know what is how to apply integration by parts. You can verify, we obtain this equation. This is the equation which is obtained by applying integration by parts. Now one thing you can clearly see here, that by in by using by applying integration by parts, the continuity demand on the field variable has been reduced. Here it is d2 y bar e by dx square. Here it is only dy bar e by dx. So requirement on the continuity of field variable has gone down. So this is also called as a weak form of Galerkin's method. So what we are exactly doing? We are applying uh, piecewise. we are applying trial functions piecewise. Instead of applying trial function for one complete domain, one complete problem, we have divided the problem into finite number of elements, and we are doing uh, uh, piecewise trial function approximation, and we are using weak form, that is we are applying integration by parts. So on account of weaker continuity requirements of field variable, this is called as a weak form of Galerkin's method. Setting I is equal to 1 and I is equal to 2, in substituting the values of I and rearranging certain terms, we obtain two different equations. Further, for simplicity, we will keep j is equal to 1, and after substituting this value, we can find these two equations like this. This is equation number 1 and equation number 2. So we obtained for one single element. We are analyzing one single element, and we have obtained these two equations. Whatever equations we obtained right now, we have written these equations in matrix form. Matrix A into matrix B is equal to matrix C. So matrix A is similar to elemental stiffness or conductance matrix, depending upon what type of problem you are dealing with. Matrix B is a nodal field vector, and matrix C is a nodal force or flux vector. We will see these things in detail. Right now, it will not be clear to you why I am writing like this, but we will soon see what is matrix A, how it is written, why it is written like this, why I am calling this as a stiffness or conductance matrix. Matrix B is very clear, that is nodal field vector y1 and y2, discrete values of solution at x is equal to x1 and x is equal to x2 when we are considering one single element. And also we will see why I am writing matrix C as a nodal force or flux vector. So this matrix A is very important. Just recall this, just see this, how it is obtained. Here, uh, one thing I would like to make clear, uh, these gradient terms that we obtained in our equation, minus dy bar by dx evaluated at x1, and second term is plus dy bar by dx evaluated at x2. Now whenever we divide our problem into number of elements, there are internal loads at which two elements are connected. For the sake of example, consider internal node P, uh, which joins two elements E1 and E2. Generally, the physics of problem is such that this gradient at internal nodes, they are equal in magnitude and opposite in sign, so that at internal nodes they cancel each other unless that some external influence acts on these internal nodes. If some external influence acts on this internal node, then this discussion is not true. But whenever no any external disturbance act on the internal node, you can consider these gradient terms, which are equal in magnitude and opposite in sign, they cancel each other. For example, consider the as shown here, internal node P. So D2 dy y bar E2 by dx evaluated at local node number 1 of element number 2 should be equal to plus dy bar E1 by dx evaluated at local node number 2 of element number 1. So they should cancel each other. That's what I want to say that. Now consider a filled problem of one-dimensional steady-state heat conduction. The governing differential equation for same is Kx, that is thermal conductivity, into d2T by dx square plus Q is equal to 0. Here Q is internal heat generation expressed in terms of uh, heat generated per unit volume. So it is in either watt per meter cube or watt per mm cube, whatever will be the system of unit. Now, before we proceed, we will consider one single element which is having the length LE. So x1 and x2 are nothing but they are varying from 0 to LE. As x varies from x1 to x2, we can say in local coordinate system it varies from 0 to LE, where LE is the length of element. So accordingly, considering the linear nature of shape function, I can write the field variable E of x is equal to n1 x t1 plus n2 of x into t2. Now by Galerkin's approach, we can write triple integral over the volume of element ni of x into, this is now residue. Keep it in mind. When we substitute this value of t in our governing differential equation, it will give the residue. So this weighing function into this residue, when evaluated over complete domain, the volume of element is your complete domain is equal to 0. That's why that's what we have done earlier. So this dv, now it is expressed as a into dx, where a is the area of cross section. In one dimensional problem, generally area of cross section is constant, assumed to be constant. So the limits of integral are now from 0 to LE. Now the equation becomes integral 0 to LE ni of x in bracket this residue k into d2t by dx square plus q, a dx is equal to 0. Separating out the terms, this equation is again written like this. By using weak form of Galerkin's method, means by using integration by parts, we can rewrite our equation like this. And as I said earlier, for any element, there are two local nodes. So corresponding to these two local nodes, I can take the value of 1 and I can take the value of 2. So further simplifying and substituting these values of I, we obtain these two equations. This is first equation and this is another equation. Now these are two gradient terms. This is one gradient term and this is another gradient term. We have seen what is the meaning of these gradient terms. At internal nodes, how gradient terms are interpreted, that we have seen, and at external node, means at the end of body, these gradient terms often represent the gradient boundary conditions. So what are gradient boundary conditions? We will see coming, we will see that. Now whatever two equations we have derived, we have written these equations in the matrix form. So this equation, this matrix equation, represent a set of two simultaneous equations. So this matrix represent the element conductance matrix. This is a nodal temperature vector. We are talking about one single element. Remember, this vector corresponds to the vector which is used to represent distribution of heat generation. Uh, Distribution means how, see, what Q stands for, heat generated per unit volume. So this heat generated per unit volume is now transferred on two nodes of single element. Part of heat generated is transferred at node number 1 and part of heat generated is transferred to node number 2. So
since heat was generated evenly in entire element, but now uh, we have represented this heat generation in such a way that the part of heat will be generated at node number 1 and part of heat will be generated at local node number 2. So this matrix represent this phenomena. This matrix represent this phenomena, and this is a gradient. This is a matrix containing gradient term. So just uh, just we have seen what is gradient term and how these gradient terms actually how they represent the physical phenomena. What we have done, we have written the equations in the matrix form. Remember our shape functions n1 and n2 are like this because our in local coordinate system x varies from 0 to LE. Here it is written LE, here it is written L, but both are both carry same meaning. So n1 is 1 minus x by L, n2 is x by L, or simply you can write 1 minus x by LE and n2 x by LE. So these were the shape functions, and in local coordinate system you can write these same functions like n1 and n2, which are shown here. So now you have the values of n1 and n2, you know the limits of integral, so you just substitute these values of n1 and n2 in the earlier equations and go on solving. So after solving these equations, you can rewrite the matrix equation in this form. So this is element conductance matrix, this is a nodal temperature vector, this is what earlier we have seen that distribution of heat generation over the nodal over the two nodes. This is the matrix which represents this phenomenon, and this is a vector containing gradient terms. So this represent gradient boundary conditions. For example, heat flux, uh, which involves for a calculation of heat flux, you need to know first derivative of temperature. So this matrix explicitly represent gradient boundary condition at external nodes. At external nodes. Now we will move towards solving a simple problem, which is a one-dimensional steady-state heat conduction problem. The problem is quite simple. There are three. It is a problem of composite slab, which contains three different slabs having three different thermal conductivities K1, K2, K3. Uh, One end of this composite slab is at a constant temperature of 20 degrees Celsius, and at another end there is a phenomena of heat transfer by convection. So as you can see here, our job is to find out the nodal values of temperature T1, T2 and T3, because T4 is already given. So the purpose of introducing this example, there are two purposes. Uh, First one is recall what we have done till now, and second one is to know how to apply the Galerkin's finite element method to the field problem where governing differential equation is readily available. Now there are three elements. We have better represented it in like this. Element number 1, 2 and 3, and there are four nodal values of temperature T1, T2 and T3. Now elemental conductance matrices are like this. You can easily find out these values K1, K2 and K3. Once you have found out K1, K2 and K3, you can assemble this to get the global matrix, which is shown here. Further, this T is a nodal temperature vector. Here we have written down the equation that is this K matrix, global conductance matrix, into this nodal temperature vector is equal to, see this right hand side. Now internal heat generation is not present, so corresponding matrix will not be there. So on right hand side, this is the vector. There is only one vector which consists of gradient boundary conditions or terms which represent gradient boundary conditions. So what is the gradient boundary condition here? The gradient boundary condition is convection, which is occurring at node number 1, uh, and how this convection is specified. It is given by H, that is film heat transfer coefficient, into T infinity minus T1. Obviously T infinity has to be greater than T1. So this is the gradient boundary condition. One more thing, another boundary condition is a fixed temperature boundary condition, that is T4 is equal to 20 degrees Celsius. So just keep in mind that this boundary condition is directly specified on the field variable itself, and this boundary condition is specified on first derivative of field variable, because to calculate the flux or heat transfer rate you have to take dt by dx into consideration. So that's why this is a gradient type of boundary condition, this one, and this is a boundary condition that is directly imposed on field variable. So this has to be treated in the same way, in a same fashion in which displacement boundary conditions are specified or are dealt in a structural problem. So cancelling the row and column corresponding to T4 and further applying elimination approach, you are all aware how to apply this elimination approach. We can obtain a reduced matrix. So this reduced matrix is like this. This is a reduced matrix after applying the boundary conditions. Uh, this this equation represents three simultaneous equations which can be easily solved. And after solving, we get these values of nodal temperatures. T1 is equal to 304.7 degrees Celsius. T2 is equal to 119 degrees Celsius, and T3 is equal to 57.1 degrees Celsius. You can check analytically also whether these values are correct or not. So you can find out the nodal values in this way. Very much for your attention, and please let me know if certain portion is not clear to you. If there are any doubts, here you can see my email ID. You can directly send me the questions. I will try my level best to answer these questions. Thank you very much. Once again, thank you very much.